Welcome to Circuit Theory Fundamentals. I'm going to take you on a journey today, not through textbooks and dry equations, but through lightning bolts, heartbeats, electric eels, and the human brain. Every electrical device you will ever design in your engineering career was first invented by nature, millions of years before any human picked up a soldering iron. By the end of this lecture, you will see resistance, inductance, and capacitance not as abstract symbols, but as living, breathing forces all around you. Let us begin. Here is the big idea. Nature runs on electricity. Every electrical phenomenon in our universe, from a thunderstorm crashing over the Bay of Bengal to the electrical pulse that just made your heart beat, to a firefly lighting up on a summer night, every one of them obeys the same three fundamental circuit properties. Resistance, which is opposition to current flow. Inductance, which is opposition to change in current. Capacitance, which is the ability to store electrical charge and so oppose change in voltage. Over the next several slides, we will explore 6 natural phenomena: lightning, Aurora Borealis, the human heartbeat, brain waves, the electric eel, and the firefly. And we will map each one to your circuit theory course. Nature is your best teacher. Let us listen to what it has to say. Let us start with something dramatic. Lightning. You are standing outside during a storm. The sky flashes. A bolt slams into the ground. It is spectacular. But here is the question I want you to ask. What exactly just happened in circuit terms? Look at this carefully. A storm cloud builds up a massive negative charge at its base. The earth below holds a positive charge. 2 conducting layers separated by air, which is an insulator. Does that sound familiar? It should. That is exactly the structure of a capacitor. 2 conducting plates separated by a dielectric. When the voltage difference between the cloud and the earth becomes too large to resist, discharge. 300 million volts released in just 0.2 seconds. That is lightning. And the Aurora Borealis? The ionosphere charging up, Earth's magnetic field guiding the discharge. Another capacitive and inductive phenomenon on a cosmic scale. Key idea for today. Capacitance is the ability to store charge. Nature's biggest capacitor is the sky itself. Now let us bring capacitance inside your own body. Every thought you're having right now is powered by a capacitor. Look at a neuron, the nerve cell that carries signals in your brain. The cell membrane separates electrically charged ions on the inside and outside of the cell. 2 conducting layers separated by a thin insulating membrane. Again, a capacitor. At rest, the inside of the neuron sits at negative 70 millivolts. When a stimulus arrives, ion channels open, rapid discharge, exactly like our storm cloud discharging as lightning. This electrical pulse travels down the nerve at 70 meters per second. Every single thought, every memory, every movement is a cascade of capacitor discharges in your brain. And your heartbeat? The SA node, the heart's natural pacemaker, slowly charges up like a capacitor, then fires an electrical pulse that makes your heart muscle contract. 1 heartbeat equals 1 charge-discharge cycle. When a defibrillator saves a life, it is a controlled capacitor discharge resetting the heart's rhythm. Now you know the circuit theory behind it. Have you ever looked at a photograph of lightning and asked, why does it zigzag? Why does it not travel in a straight line? The answer is resistance. Air has very high resistance, so current cannot simply push straight through it. Instead, lightning probes the air, seeking pockets of moist air, dust, and particles that have lower resistance. It zigzags along these low-resistance channels. Tall trees and metal towers offer lower resistance paths than open air, which is why lightning rods work. They give lightning the easiest path to ground. Now look at the human body. Dry skin has a resistance of approximately 100,000 ohms. Wet skin drops to 1,000 ohms. Deep body tissue is only 300 ohms. Water drops your body's resistance by a factor of 100, which is precisely why wet hands and electricity are a dangerous combination. And in the sea, salt water has very low resistance, giving electric eels the perfect conducting medium for their discharges. Resistor. In your circuit, it is any element that opposes current flow. Let us now see resistance at work in 3 systems of the human body. First, muscles. When a motor neuron fires, current flows through muscle tissue. The specific resistance of muscle fibers determines how much current causes contraction. Physiotherapists exploit this with TENS therapy, transcutaneous electrical nerve stimulation, applying controlled current to rehabilitate muscles. Interestingly, bodybuilders have lower bioimpedance than untrained individuals. Their muscles are better electrical conductors. Second, the brain. An electroencephalogram or EEG detects tiny voltages from brain activity through the skull. But the skull bone has very high resistance. It filters and attenuates brain signals. When skull tissue is damaged, its resistance changes, a fact neurosurgeons use in diagnosis. Third, the heart. An electrocardiogram or ECG reads electrical signals from the heart. Different tissues, fat, muscle, and blood, each have different resistances. Cardiologists read these resistance patterns to detect blockages and heart attacks. Your body is not just using electricity, it is using circuit theory. Now let me introduce you to the most impressive bioelectrical engineer in the animal kingdom, the electric eel. This animal generates 600 volts, that is more than double the voltage of a standard Indian wall socket. It can deliver 1 ampere of peak current, enough to stun a horse. How? The eel has approximately 6,000 electrocyte cells lined along its tail. Each cell generates approximately 0.1 volts. They are stacked in series, exactly like batteries in series in your lab experiments. 6,000 multiplied by 0.1 volts equals 600 volts. The discharge lasts only 2 milliseconds. Then the eel recharges. Now look at the circuit equivalent. The electrocyte stacks are capacitor banks, storing charge in parallel and discharging together. The ion channels are the switch or trigger. Salt water is the low resistance load, and the rapid current surge creates an inductive spike. This is not just biology, this is a complete R.L.C, pulse generator circuit, and engineers have copied this exact topology to build industrial high voltage pulse generators. Nature filed the patent first. The electric eel is spectacular, but it is not alone. Let us meet 3 more bioelectrical engineers. The firefly. That gentle light on a summer evening is controlled bioluminescence, a biological switching circuit. Oxygen reacts with luciferin, controlled by precise neural switching signals. It is a biological oscillator circuit, pulsing at a species-specific frequency to attract a mate, the shark. Sharks have a sixth sense called electroreception. They detect the tiny electric fields generated by the muscle activity of prey, even when completely hidden in sand. The sensory organ is called the ampullae of Lorenzini, essentially a biological electric field detector. Sharks can detect fields as weak as 5 nanovolts per centimeter. That is extraordinary biological sensitivity. The bee. When a honeybee lands on a flower, the flower holds a slight positive charge from the Earth's electric field. The bee carries a negative charge built up during flight. The pollen jumps to the bee electrostatically. The flower even updates its electric field after a visit, signaling to the next bee. This flower has been recently visited. Capacitance, switching circuits, electric field sensors, all invented by nature, billions of years before your first circuit theory lecture. We have explored capacitance and resistance. Now let us look at the most counterintuitive of the 3, inductance. An inductor opposes changes in current. It stores energy in a magnetic field. And the greatest inductor in our solar neighborhood is the Earth itself. The Earth's molten iron core carries massive electric currents. These generate the planet's magnetic field. This magnetic field behaves like a giant inductor. It opposes sudden changes in the flow of charged particles from the sun. When a solar flare strikes, there is a sudden surge of charged particles. Earth's inductive magnetic field guides them toward the poles. The result is the Aurora Borealis, the northern lights. Faraday's law at a planetary scale. When a very intense solar flare hits suddenly, the rapid change in current induces massive voltage spikes in power transmission lines on Earth, the same mechanism as transformer induction, and can knock out entire power grids. Now look at the human brain. Neural circuits create oscillating current loops. Like an R.L.C circuit, these loops resonate at specific frequencies, producing the theta, alpha, beta, and gamma brainwave rhythms that your EEG measures. Our brain is an oscillating inductor network, and Earth wraps around it like a planetary scale inductor shield. We have studied resistance, inductance, and capacitance separately. Now let us bring them together, because in nature, they always work as a team. Consider a lightning storm. The air's resistance determines which path lightning takes. The magnetic field of the lightning channel acts inductively, opposing the rapid rise of current. The cloud-to-earth gap stores the charge capacitively until it cannot hold anymore and discharges. Engineers copy this exact behavior in a surge protector circuit. R limits the current, C absorbs the spike, and L filters rapid changes. Consider the human heart. Tissue resistance controls current spread. The spiral muscle fibers create inductive current loops. Cell membranes charge and discharge capacitively every single beat. Engineers copy this in a pacemaker circuit, and the electric eel. High R, dry land, weakens its discharge. Low R, salt water, makes it lethal. The electrocytes are capacitors. The rapid buildup is inductive. Engineers copied this topology for industrial pulse generators. Everything in circuit theory has a living counterpart in nature. The human body is the most sophisticated circuit board ever assembled. Let us map it, system by system. The brain. The skull bone presents a resistance of approximately 100,000 ohms, acting as a high-resistance filter between brain signals and your EEG electrodes. Neural current loops create the inductive oscillations we measure as brain waves. Every neuron's cell membrane is a capacitor of approximately 1 microfarad per square centimeter, charging before each action potential fires. The heart. Myocardial tissue resistance determines how the electrical wave propagates through the heart muscle. The spiral fiber arrangement creates inductive current loops that give the heart its rhythmic stability. The SA node membrane charges slowly and discharges, 1 capacitive cycle per heartbeat. The muscles. Motor neuron signals drive current through muscle fibers whose resistance determines contraction strength. Contraction itself creates circular current loops. Inductive behavior. The neuromuscular junction acts as a capacitive interface between nerve signal and muscle response. R.L.C. everywhere, always, simultaneously. Let us now look at what happens when the body circuit is disturbed and how doctors use circuit theory to assess it. Dry skin has a resistance of approximately 100,000 ohms. The keratin layer is an excellent insulator. Wet skin drops to 1,000 ohms. Body interior, blood, muscle, organs, sits at around 300 ohms. A current as small as 50 milliamps through the chest can cause ventricular fibrillation. 10 milliamps through the arm can lock the hand onto a live conductor. The muscles cannot let go because the current is controlling them. A defibrillator delivers approximately 200 joules of capacitor energy to reset the cardiac rhythm. That is circuit theory saving lives in the emergency room. And now, in hospitals and even in smart weighing scales. Bioelectrical impedance analysis, or BIA, passes a tiny safe alternating current at 50 kHz through the body and measures R.L.C values. Fat tissue has high impedance. Muscle and blood have low impedance. Engineers measure your body the same way they measure a circuit component. Let us consolidate everything we have covered today. Capacitor stores and releases electrical charge, opposes change in voltage. You find it in the storm cloud above the earth, in every cell membrane, in the SA node of your heart, and in the electrostatic pollen transfer of a honeybee. Resistor opposes flow of current, converts energy to heat or useful work. You find it in the zigzag path of lightning, in dry versus wet skin, in the low resistance of seawater, and in the high resistance of skull bone. Inductor stores energy in a magnetic field, opposes change in current. You find it in Earth's magnetic core, in the Aurora Borealis, in the spiral fibers of the heart, and in the oscillating current loops of your brain. Remember this always. Every electrical device you will design in your engineering career is nature's own circuit, miniaturized, refined, and put to human use. You are not learning new laws. You are learning to read the laws nature already wrote. As a scientist once observed, the most exciting phrase in science is not eureka. But that is funny. It behaves just like a circuit. Then, for further reading, I recommend NPTEL's Basic Electrical Circuits by IIT Chennai, Khan Academy's Electrical Engineering series, the Veritasium video titled The Big Misconception About Electricity on YouTube, and the book The Body Electric by Robert Becker on bioelectricity. Thank you very much.